thank you all for coming to today's talk. There's feedback? Is that okay? Um, Today I'd like to talk about partly my research, but also partly my astronomy journey, particularly down in Chile, where I took this basically time series shot of the night sky from the Paranal Observatory, run by the European Southern Observatory. And what you see is the night sky as you see in the Southern Hemisphere. I think it's much more beautiful than what you see in the Northern Hemisphere because it's not just stars that we see, right? The stars that make up our Milky Way, which we see in the Northern Hemisphere, but we also see two other weird things. One feature here, one feature up here. These are galaxies, collections of stars like our Milky Way, but they're actually really close to the Milky Way, right? Or basically galactic neighbors, if you will. And it's just crazy. You can see these with the naked eye just by walking out. Almost the exact same structures. This is about I think it's like a 1/10 of a second exposure with my camera on each frame that I took here. So it's incredible to look at. And my research is all about trying to understand how these galaxies change with time by looking at their chemistry. So this is the first time that I'm giving a public talk, and I'm a bit nervous. So I'd like to invite you all to take a deep breath with me. So inhale and exhale. And something that you might have not thought about before is as you're breathing in the oxygen that fuels all the burning of carbohydrates and stuff to fuel your body, you're breathing in oxygen that came from the carbon that is in your body and the hydrogen that's in your body that's being broken down. All these atoms were once inside a star. But what's even crazier is at least one atom that you breathed in there when you took that breath came from oxygen that was once outside our Milky Way galaxy, somewhere between us and these two galaxies, which are hundreds of thousands of light years away from us. Okay? Stars and how they produce all the elements in the universe are very fundamental to us on Earth, but also to understanding how galaxies change with time. So that's essentially the precious metal side of thing, right? Oxygen's precious to us. I know it's not a metal, it is to astronomers. And I'll talk about other more metal-based definitions later. But I also want to talk about the other part of my title, galactic rainbows. Okay, what do I mean by this? Well, essentially, it's a spectrum. What is a spectrum? Okay, spectrum, we are used to seeing kind of in our day-to-day, if we shine light through a prism, it breaks out into a rainbow. This is a spectrum of light. We see all the colors that we can see with our naked eye. It's not just purple all the way to red, but there's other parts of the electromagnetic spectrum. We got gamma rays, X-rays, ultraviolet, these really high energy sources of light that are dangerous to us. Thankfully, the atmosphere blocks all this stuff from light that comes from outside Earth. But we also have more redder sources of light, infrared, radio waves. Who knows? I guess there's some young people in the audience that probably don't know what a radio, AM and FM radio are. And that TV used to come off radio signals. But we have all of these different kind of types of light that we can look at and get a spectrum. Now, we're kind of used to taking a spectrum of something like a light bulb or the sun, and we send it through the prism and we get all the colors that we can see in the rainbow. But it's not just as simple as that. Has anybody ever taken a spectrum of like a neon light? Or I see a couple hands come up. If you haven't, I don't know if it's neon, I think it's hydrogen and something else. In the back corner of the display in the other room, you can go and take this, and I encourage you to go do this yourself after the talk. You can send the light through essentially a prism, and what you see is actually not a rainbow. You see all these different colors broken up. But as you notice, there's no blue, there's no purple. It's a lot of red and a little bit of green and a little bit of yellow. Okay, that's what you see when you look at neon. You can look at other elements on the periodic table, things like hydrogen, helium, sodium, mercury, and each one has its own set of colors that the light gets broken down to. Okay, so essentially, if you want to look for a particular element, you can basically identify it when you take a spectrum of it based on what colors show up, each of these little sets of lines. Okay? We actually had a great experience of seeing something like this with the naked eye. I hope you all did. About a week ago, we had the aurora. All right, so this is a photo I took at the Mount Doug beach. And all these colors are just caused by elements in our atmosphere getting energetically excited and emitting based on these fingerprints. All right, so the green is coming from oxygen, the hydrogen and helium is the purpley colors, the red is nitrogen and hydrogen in our atmosphere. Again, this is just really strong particles coming off the sun, bombarding the surface of our atmosphere and exciting all these elements that are in our atmosphere and causing these colors. Okay? You can take this one step further and you can take spectrum of the sun. Unfortunately, we didn't get an eclipse like this a few weeks ago, but I took some liberties here, and this is what you would get if you took a spectrum of the sun. We get all this color coding, right, from red to blue, and I should explain that the sequence along each row is just a gradual change in color, and it's just split up into bunches of rows because otherwise this would extend way, way off the screen. But it's not just the solid colored rainbow that you see. You see all these little black lines on top of it. This is absorption from the surface atmosphere of the sun and all the little elements that are on the surface of the sun. So there is some sodium, which are these kind of yellowy orange lines, those very dark lines you see in the yellow. That's sodium. And there are bunches of other elements. In fact, helium, which we didn't really know about on Earth until somebody took a spectrum of the sun and said, hey, what are these weird lines? I've never seen these before. That's how we discovered helium, hence the name helium, helios, Greek for sun. All right, so essentially we can get chemistry by looking at the surface of stars and understand kind of where that is coming from. Now, stars sure have this chemical content on their surface, but they're actually, as they call it, the cauldrons of the cosmos. Now, I apologize, it's getting a bit technical with the periodic table in some sense, but all the elements other than hydrogen and helium, and a couple other ones, but I won't get into the details, are made inside a star through nuclear fusion or some other process. Okay, so this is how we get oxygen. Oxygen is made from stars that are about 10 to 100 times the mass of our own sun. Going through nuclear fusion, burning things like helium at the cores of the star, producing oxygen and carbon and everything else, and then that slowly gets pushed to the surface. Eventually, these stars explode, push all the material out that they've created through nuclear fusion, and that gas sits in the galaxy, sitting around. Maybe it gets outside the galaxy, like that oxygen atom that you breathed in. Sits around, eventually that gas cools, forms a new star. Now you got a more enriched star with all the elements on the surface. That's how we get the spectrum like we see on the sun. Okay? And each type of star produces different amounts of different elements. So oxygen, which you see is completely colored blue, it's made in these very massive stars, again, 10 to 100 times the mass of our own sun. Our sun is going to produce a lot of carbon and nitrogen, the green colors essentially. And those suns that you see on Tatooine in the Star Wars universe, the two suns that are together, they're going to produce a lot of iron, okay? And those red colored elements. Okay? So we could what astronomers do, and this is what I do in my day-to-day, is use each of these elements, whichever one I see, and try and infer what type of star that came from, and try and understand why galaxies are changing. But this is really nice. There's a lot of elements we can see, but it gets a bit complicated, because if we try and understand what our universe is made out of, 78% of matter that we know, like this table here, yourselves, the air, all that stuff, 78% of it is mostly hydrogen, 20% helium. 2% of the rest of the matter in the universe, the oxygen that you breathe in, that carbon that you're made out of, all of that stuff is 2% of the known matter in the universe. Okay? There's not much of it. Right? It's mostly hydrogen. A little bit of helium, a little, even less of everything else. But it's not, doesn't just stop there. This is known matter. Go a little bit more complicated. This is the pie chart of ignorance that we like to call. Okay? Of the stuff on the periodic table, that's only 5% of the total mass of the universe, as we understand it. We can go a little further. We can try and say, okay, we know Newton told us how planets go around stars, and that basically tells us how stars go around the center of galaxies. And we go and we try and say, okay, for this amount of material, how fast do stars move? We try and count it all up. That doesn't make sense. Why are stars moving the way they are when we only see so much mass? Well, this is what gets labeled as dark matter, is this extra mass that is needed to make Newton's laws of gravity work. Right? Newton's laws of gravity work here on Earth, but we need some unknown matter to explain it in galaxies. And then there's this other stuff, 68% we label as dark energy. This is just the same pie chart with a little cartoon, where it's just something that's driving the expansion of the universe. And I'm not going to talk about too much of that, but this is why it's called the pie chart of ignorance. We only know 5% of what exists in the universe that we could actually see and interact with. Okay? So now let's move on from, this is what the universe is made of, at least that's what we think it's made out of. How do we go about doing this? Particularly as astronomers, right? So we can take a spectrum of a star or a galaxy and whatnot, and look at the surface chemistry by looking at what light is missing, what colors are missing. It's not just, we don't do this with a prism. Prisms absorb a lot of light. They're very ineffective. They can have impurities. It deflects things. They're not very precise. Okay? So while this nice picture of a prism is great for a talk, it's not great for doing astronomy. And this is where we go to something else. We'll use a diffraction grating. Now you can go again to the demos in the corner of the displays out there, and you can actually look at diffraction gratings to get it, because I don't have any to share with you. But they're essentially like the backs of CDs. Okay, so these CDs, these physical media, again, don't know if these things still exist to some of you. They all have little tiny etchings on the disk to store the information, right? Basically ones and zeros. Is there a little etch or isn't there not? And these tiny little etchings, when light comes in and hits that, it creates a rainbow. And that's why you see these rainbows on the backs of CDs, is essentially their diffraction grating. And this is what astronomers use in their spectrographs. So I just want to show a couple of spectrographs that I've worked with. One was made here, just down the hill there, at the National Research Council, the NRC Hertzberg. The ghost spectrograph. This is an image of the spectrograph. You can see they shined light inside the spectrograph, and you can see the light bouncing off the grating, the diffraction grating, and that's what's producing that rainbow in there. So this is a high resolution spectrograph, which means you get very, very fine details, like these lines, very, very precisely. And it was installed on the Gemini South Telescope in Chile, which Canada has, I forget, like something like a 20% partnership with this telescope. And I was down there helping the team that was here based up here, getting this up and running on the telescope and taking some data. And taking some of the first spectra on sky with the spectrograph. The other cool spectrograph, which I just think is really fancy, is MUSE. This is a crazy spectrograph on the Very Large Telescope in Chile. This is one of the ones that I worked at. I didn't get to actually take data with this personally. But it's not just a single spectrograph where you point it at one, like GHOST, you point it at one star, you get one spectrograph. How this one works is you get a bunch of fiber optic cables and you put them everywhere on the sky, and they're basically a fairly large area on the sky. You're taking, I think it's about 40,000 spectra, pixel by pixel, and each fiber optic cable takes that light and passes it through to 24 spectrographs on the back. That's why this thing looks like the back of Doc Ock, if you're a Spider-Man person. All these cables are the fiber optic cables coming off the telescope and feeding each of these spectrographs. So not only do you get that spectrum on each kind of pixel in the sky that you're looking at, but you also get an image, and you can do some really cool things with that. And it's actually one of the most oversubscribed instruments. A lot of people are asking time to use MUSE, and I think it's about 1 out of 11 requests get time on MUSE. It's very highly demanded because it's just such a cool instrument. It also has a really cool feature that it has a telescope. It's mounted on a telescope with 4 lasers. Okay, when you look up at the night sky, the stars twinkle. Well, that's terrible for astronomers because that's the atmosphere blurring these the stars. If you want very precise measurements, you want to account for that turbulence in the atmosphere. So what astronomers do, they shine lasers up into the sky, they make artificial stars, and they try and reconstruct that motion of that artificial star to basically improve their images. So this is a picture I took just walking out one night when I was taking a break from my observing, and you just see these things are bright. To give you a sense of scale, this is an 8-meter telescope diameter mirror. There's me standing underneath this 8-meter mirror. There's MUSE, roughly to scale. This is roughly to scale. I don't actually have the measurements. But just to give you a sense, those laser beams almost look as big as my head. So they're really giant, and they just go flying out into the atmosphere to make these artificial stars. Digressing a little bit from the science, I just want to tell you a bit about life kind of working at the European Southern Observatory. So it's based at the mountain Cerro Paranal. It's at basically 2,600 meter elevation. The observatory has 4 8-meter telescopes. So 4 of these behemoths with different instruments. 4 1.8 meter telescopes. You're going to see, you might go look at the telescope here on site. There's 4 essentially these that you can move around in a little grid. And a 4 meter and a 2.8 meter telescope. And it costs about 90,000 euro per day to run this facility. So time on this telescope is very, very expensive. And it's very, very nerve-wracking sitting there, hoping you don't make a mistake when you click a button, observing, because you know you're going to get in a bit of trouble if something bad happens. So this is the residence where all the astronomers and all the staff on site sleep. I forget, there's hundreds of people on site at any given moment, engineers, astronomers, logistical staff, all that sort of stuff. Lots of people. Anybody recognize this building? Yeah, I got 1, 2 hands. Any James Bond films? Yeah. Quantum of Solace. Thankfully, my room's on the other side. So it's cool because there's actually a picture of Daniel Craig autographed that's hanging in the residence building. So yeah, this is used for some films as well. And this is the control room. This is actually, I just grabbed a random photo online. It happened to be the same station that I worked at. So each telescope has its own little station. You see a lot of monitors. There's a lot of computers. There's one telescope operator who controls the telescope, makes sure the telescope is safe. one astronomer who is kind of hidden behind this person here, which was my role, basically picking which things to look at on behalf of people around the world. Or sometimes we have a visiting astronomer, that other person in the photo, and you're helping them take their observations. You're also monitoring the health of the instruments, making sure nothing's breaking. It's very expensive. And it's just evaluating kind of the feasibility of observations to make sure that when people come and they observe with these telescopes, they're going to get data. And they're not trying to do something too crazy that they're going to basically waste time. Again, very expensive facility. The typical kind of working hours were 8 to 14 hours, basically nonstop. I say nonstop. I'd still go out and take photos and take breaks and stuff. And it'd be 6 to 14 shift stuck up in the Atacama Desert in northern Chile before I get to go home. And I'd have to do 80 nights, and some staff do 100 nights a year. And again, I mentioned these breaks. I have a nice camera to go out and just take beautiful images and time lapses. So you can see it's, unfortunately the lighting's a bit hard to see this, but you can see the one telescope rotating with the lasers and the Milky Way moving in the background. And here is the large Magellanic Cloud, one of our neighbor galaxies, again, that you can see with the naked eye. So, coming back to the science. How do we see what the universe is made out of? We take spectra of stars in our own Milky Way or in nearby galaxies, which is actually one of the first spectrum taken with the GOES spectrograph, the spectrograph made down the hill here. This is an example image from that with some of the lines, absorption lines labeled with hydrogen in the blue here, some calcium and whatnot. Okay, so that's one way to understand what the chemistry of galaxies is, by looking at stars. But stars get very, very small, really very, very, very fast. You can only look at stars in our own Milky Way and these nearby galaxies. But if you want to understand how the universe is changing over the cosmic history, 13.6 billion years the universe has existed, you want to be able to look at other galaxies. Now, other galaxies in the so-called, I'll call it the teenage universe, or when the universe was a baby, are about the size of Chris Hadfield on the International Space Station as we're sitting here in the parking lot, if it's hopefully clear tonight, looking up and trying to look at this. The galaxies are very, very tiny. Another equivalent, because I know I invited a couple curlers to the room, is if you were to throw a curling rock and you're looking at your skip's broom, you're standing in the downtown harbor in Victoria, your skip is standing in Langford, right? So this is about a 4-centimeter target that you're trying to aim at. It's very, very tiny, okay? So how can we do this? So what my research focuses on is using what I like to call cosmic lighthouses to probe the fog of galaxies, okay? So what are lighthouses? Lighthouses are basically some sort of beacon for telling us if there's fog or land and whatnot around us, okay? So rather than looking at a lighthouse in reality, what I look at are quasars, these very, very bright point sources, quasar coming from quasi-stellar object. So they look like stars, but they're actually galaxies all over the universe. And they're actually quite bright. So that light goes through a galaxy, hits all the atoms inside that galaxy, and the gas that's being pushed out by stars, that gas absorbs the light according to the colors of the individual elements that are in that gas, and then we observe it. I use the Hubble Space Telescope and the very large telescopes that I talked about in Chile to understand the chemistry of that gas. In particular, I'm hoping to go and find evidence of what the first stars in the universe look like. Because if you go and you do some simulations of stars and whatnot, you need a little bit of carbon, nitrogen, and oxygen to get stars going, to start fusion. But in the first stars to form in the universe had no carbon, nitrogen, oxygen. The Big Bang only produced hydrogen and helium. So how do you get there? Okay, something weird has to happen. And if something weird has to happen, it must mean that maybe stars are super duper massive, thousands of times the mass of the sun, hundreds of thousands of times the mass of the sun, if you believe such ridiculous numbers. And that's going to have influence on that chemistry, what fusion takes place. So what I'm doing is hoping to find those chemical signatures, then tell the people who do simulations, this is what I found, how do you reproduce that? So we can understand what the first stars look like. Something even more crazy is trying to understand dark matter. I just told you at the beginning of this talk that we can't see dark matter, right? We don't have a way to visually see it, but can we understand something about it? Now, one of the cool features about when you take a spectrum is when you look at those lines, the width of those lines is actually a thermometer. It tells you something about the temperature of the gas that those lines are being created in. So if we just kind of think very simplistically, galaxies reside in a sphere of dark matter. Let's just call it a balloon of dark matter. Okay. If dark matter is something that kind of collides and stuff like that, it's going to heat up a bit. So you can think of it, this balloon of dark matter, as being warm, kind of big, this kind of picture of a balloon getting stuck in liquid nitrogen. Right? When it's warm, it's nice and big, but when it gets cold and stuck in the liquid nitrogen, it contracts. So the size of this balloon is basically telling us, basically the size of this material around galaxies is telling us something about whether dark matter is warm or cold. Does that make sense? Okay, good. I'm getting a lot of nods. This is the slide that I was worried most about when I was designing this talk. So the way to do this is to precisely measure the widths of these lines and the frequency of detecting these lines in the universe. And the precision of measuring these lines has to be down to basically the width of a single hydrogen particle. Okay? Very, 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 very precise measurement. So how do we do this? Well, we designed a very super stable spectrograph that can do this. And I've been working, I was fortunate to be on the instrument team of the espresso spectrograph on the Very Large Telescope. So I was actually involved with making sure, like, designing new modes of operation for this. In particular, I got to test it on observing a faint quasar, so I could do my science. And one of the coolest things about it is that I mentioned these 4 telescopes at ESO, Paranal. All 4 of them can be combined to feed the single spectrograph. Through mirrors and fiber optic cables, all the light comes into each telescope, bounces off a bunch of mirrors into a room. This thing's about twice the height of a human, just for reference. And all that light gets fed into the spectrograph, and we can get a lot of light in there and get very, very high quality spectra to be able to go and look to see if we can measure the temperature of dark matter. Okay. There's other cool things you can do with it. I can never remember the acronym for espresso. It has something to do with rocky planets, the R and the P. And measuring, you can use it to measure the chemistry of the atmospheres of planets orbiting other stars. As the planet passes in front of the star, you observe it with espresso, you see the absorption of that atmosphere of that planet, and you can understand the chemistries of other worlds and hopefully search for life. So that's what bulk of time being used on espresso is actually observing planets. But I have, so happy about this, we have 170 hours to observe quasars to look for things like dark matter and the properties of first stars. So with that, I appreciate you listening. And before I end, I just want to quickly show the periodic table as I've detected it through quasar light. I think I've seen chlorine. I would never publish a paper to say I've seen chlorine yet. But all of these elements that you see, that is what I've detected in the teenage universe. This is 10 billion years ago, just to give a number of our 13 billion year history. So thank you for listening. And I'm happy to take questions. I'm not sure if that's what you're coming up here for, Ben. Okay.
Questions?
I hope there's lots. I hope I've confused a couple things. Yes.
I've heard news on NASA websites that there is signs of life on one of Jupiter's moons, Europa, and I'm just wondering what types of elements were found on.
So Europa, from what I remember, and this is going back like 15 years, I haven't really thought about it much since then, it's basically an ocean moon with an icy layer. So just because we think there's a lot of water on there. Now we like to think because life on Earth requires water. If there's water on a planet, a lot of it, there might be life. So that's kind of the logic behind it. I'm not sure anything more beyond that if they found oxygen, but everything is based on kind of like the surface and some of like the crystalline features, ice and whatnot. But I think they really want to send a drill effectively to Europa, drill down and understand what's going on in Europa. So I think that's the plan for NASA. Interesting.
I don't know how they could possibly.
Yeah.
Because if you look at the galaxy, you see this tiny bubble of everything we've ever seen. The galaxy is pretty big.
No worries. That stuff I don't really know about. I'm way out there in this world, right? As I'm talking about things 10 billion years ago, not something that we can see with like 9 light minutes.
It's something you have to realize that every single star that you see is close by, relatively speaking. But the ones you see in your naked eye, they're pretty close by. They're all in our galactic neighborhood. And that's also true for all the exoplanet discoveries. And some of them are correct. Just moving up into the night sky would be some sort of no, you won't see those because your eyes aren't very good. Sorry. You need a big telescope to get that.
Yeah.
Maybe I missed this, but with the elements from the team, were you saying that it's like our universe kind of the team, or
Yes, our universe. So essentially, quasars are really far away. Okay, we can see them up to about 11 billion light years away. Now, it takes 11 billion years for that light to get from our quasar to us. So when that light was emitted, the universe was about 2 billion years old. So that is how we get a timestamp, essentially, on our measurement, is the further away we look at something because of the way the universe expands and all that sort of stuff and evolves, the time it takes to get that light to see it, where we can see that light, is basically a timestamp of when that light was emitted. And that's how we know, okay, this galaxy had this element in it, and now it's taken this time for that light to get to us.
Go back a little bit.
Yeah, the slide where it said that 70% of what we know was that hydrogen.
Yes.
And then nitrogen said yes. But then when we were a teenager, there was
There's some helium. The Big Bang creates hydrogen and helium, but there wasn't as much. This was probably closer to like 0.5%. Oh, these are things that I have physically seen with my naked eye in spectra. There's just less of it. So, so there's right now, as we go out and we look at the chemistry of the sun, we count up how many atoms of cobalt, carbon, and gold exist there. And if we were to go and look for that in the early universe, it'd be about 100 times less, thousands of times less.
what is like the pace of the heavier elements created over time? Like were most of them created early soon after the Big Bang, or is it steady? Like is the Earth increasing or increasing?
That's a very good question. It really depends on the types of stars that are formed. the simple answer. The more complicated thing is stars, when stars are born, they kind of form in groups and of different masses. So there's going to be a lot of these little tiny stars that are smaller than their sun, fewer sun-like stars, but there's going to be even fewer massive stars. Now the massive stars live fast and die hard, okay? They live about 10 million years, like this, maybe even less, and then they explode. So there's some gap, right? The star has to evolve through its fusion processes and then explode and dump all that material back out. But it's the most massive stars that go first. So if we think about the early universe and we believe these models that I don't know if I believe, where you have these 10,000 mass stars exploding, I don't know how quickly they explode, but presumably really fast, they're going to be the first things to pollute the universe. And then things like our sun and the binaries will eventually pollute. So in fact, just as a quick aside, looking at elements like oxygen, magnesium, silicon, we go and we measure that and we compare it to the amount of iron that's produced. You can see oxygen, magnesium, silicon's mostly blue, but oxygen, magnesium, completely blue. Iron has some red in it. This is essentially a chronometer. It's telling us kind of when the most massive stars exploded and when stars like the binary sunset in Tatooine explode, because that's what produces the iron.
Okay, we'll take one more because Trystyn has to do it all over again. So he needs a break.
That's a good question. I do not have any intent. Why do I say that? It's even harder to get time on James Webb compared to Muse. I'm fortunate to get a little bit of time with that. But also, it's got a short lifespan, so it's just very competitive, and I just don't, I don't have a good enough project to be able to do that. That being said, there are people in my field that are getting time, or trying to get time to understand things, but unfortunately, the big thing is you need a really high resolution spectrograph to do the science that I'm doing. James Webb spectrograph is, I'll say garbage compared to that. I don't want to just diss James Webb. It's coming out with beautiful images, beautiful science results, but it's not as precise as some of the spectrographs that I use.
Thank you very much.